David, for inviting me to speak today. My name is Mateja Jamnik, and I have been in the computer lab in Cambridge for quite a while, but I've done my PhD in Edinburgh and I've traveled around a bit. It's a pleasure to be here, and those of you who are very observant will notice that the title is slightly different to what it says on the program, but actually it's the same type of work, so you're going to hear the talk that I promised in the abstract. And those of you who have been in Cambridge last week, don't worry, you don't have to switch off. In fact, don't worry and do switch on, because it's a different talk to last week. So I work in the area of artificial intelligence, and I'm a mathematician by training. And I'm interested really in studying how humans do mathematical reasoning, how they solve problems, in particular using things that perhaps a more formal community would consider informal methods, like using diagrams and so on, or using symmetry or using analogy. So this talk will be an example of studying a particular aspect of human reasoning in using diagrams, in which, we would consider, and I'll show you some example, hopefully you'll agree with me, we would consider to be intuitive mathematical reasoning, but if you try to formalize those things in existing theorem provers, you would have quite a bit of, first of all, losing a lot of intuition, and secondly, sometimes not even be able to formalize it necessarily. So, and I'll show you some examples. And my hypothesis really is, or the question that I want to ask is, can we make machines reason in the same way that humans do, and can we capture that intuition? So this is the outline of my talk. I don't know, where should I stand? There? Or there? So I'm going to move around, I think. I'll give you some ideas about what's driving my work. And some examples of how we can use diagrams to solve problems. And then I will address an issue of how you can combine different types of representations in trying to prove the same problem, and talk about accessibility of this kind of reasoning. So let me start with some motivation. So I'm going to present you, probably most of you have seen this before, but it's called mutilated checkerboard problem. And it's an example of something that for humans it's very easy to see, and hopefully you will see. If you haven't seen it before, you can't shout out if you've seen it before. But trying to automate this completely, it can be done, but it completely loses all the intuition behind this human solution. So the problem asks, we have a mutilated checkerboard, which means it's mutilated because we've taken two diagonal corners away from this checkerboard. Yeah? And the question is, can you cover this mutilated checkerboard with dominoes? And a domino is a 2x1 rectangle. Yeah? And so you can try it to tile this checkerboard in many different ways. You can go row by row, and you will see that you'll have two squares left over, or you can go around and around, and you can use various methods. And most of them will demonstrate that you can't cover you can't find the solution. But why is that the case? So let me give you an example of changing the representation, which is, well, let's color the checkerboard black and white like a chessboard. And therefore, so your domino now is one black and one white square, yeah? And now it's immediately obvious that when I took away two diagonal squares, I took away two white squares. But if I want to cover this board with dominoes, I have to have the same number of white and black squares. So I will never be able to do that. And so the intuition is so simple, right, for us to see that. But if you were trying to do this in your favorite flavor of your theorem prover, and formalize it, the intuition is lost. And this is probably 1/5, or probably even less, of a whole proof of the formalization of the proof of this theorem. Yeah, so I want to capture those types of intuitive characteristics of human reasoning on machines so that we can make machines reason in that way. So what do I want? We want to make AI systems more human-like in reasoning. We want to make them more accessible. That's the kind of a long-term goal. And in the process, we want to understand how people do it, And we want to build tools which will enable us to study this in humans and help us then use these machines, these systems, to solve problems in these types of intuitive ways. So the question is, if I find, like in the mutilated checkerboard example, if I find the right kind of representation to my problem, then the solution becomes almost trivial and becomes easy to find. And that's one of the things, for example, that Polya has also been championing. And another question, can we do this on machines? Can we do this kind of reasoning on machines? So let me give you an example now of the types of diagrammatic examples that I have been looking at. So here is an example of a theorem about the odd natural numbers, and it says that the sum of the first n odd natural numbers is n squared. And here is a visual proof, a diagrammatic proof of the theorem. So I've taken an example where n equals to 6, so I've got a square of size 6, and then I split it up into what I call a sequence of L's. And each L is a subsequent odd natural number, because I've counted this vertex edge once, twice, so that's my 2n, but this vertex was counted twice, so it's 2n minus 1. So this is something really easy to see and understand, and I can probably take it to secondary school and demonstrate it to the kids, and they won't need to know anything about induction to understand that this is a solution for the problem. But more than that, you can also see that this will, whatever instance I take, the proof will be the same, and it will hold, and it is a true explanation of, or it's a correct proof of the theorem. So this is the kind of theorems that I want to be looking at, and I want to develop reasoning techniques that will enable systems to find exactly solutions in exactly the same way as I've now presented to you. Build the system so that they can, once automated, they can even discover solutions like this that we would consider to be intuitive, and perhaps even that we haven't seen before. And obviously, these kind of systems can then be used to explore how people are reasoning. So there's various examples out there that we could look at, and there's lots of books about these diagrams where you see a picture and it says "behold," and Roger Nelson wrote a few books about that. And so this one is about Pythagoras' theorem, and I'm sure that some of you might have seen this. At least 1 out of 8 visual proofs that I know of about Pythagoras' theorem. And it basically says that when we have a right angle triangle, these are the two sides. This is the hypotenuse, and the square on the hypotenuse is the sum of the squares on the other sides. And so if you, the visual proof goes that if you build a square like this of size a plus b, you get inside 4 identical right-angled triangles with these proportions. And here's the square on A, and here's the square on B. Now imagine that you are kind of sliding these triangles around. So this one goes up here, this one goes up there, this one goes down here, and this one stays here. You can see that the emergent thing is the c square. The invariant are all these 4 triangles, and therefore a square plus b square must be c square. This one I've showed you already, and here's another one, which is basically about the sum of geometric sum. And it basically says that 1/2 plus 1/4 plus 1/8, so 1/2 to the power of I, infinitely long, is equals to 1. And here's the proof. So I'm going to take a square of size 1. So this is my 1 here. And I'm going to cut it down the middle. So this area now is 1/2 of my square. So that's my first one. And then I'm going to take the remaining bit of the square and cut it down the middle again. So I get 1/2 times 1/2, which is my second one here, 1/4. And now I'm going to take the remaining bit of the square and cut it in half again, and so on and so on. And you can see that if I do this dot, dot, dot number of times, infinitely many times, I will complete the square. So there's lots of different examples of this, but which ones am I going to look into in particular? Well, I'm going to look at this second category where we're talking about natural numbers. So we have a discrete space and we have a notion of a universal quantifier because, for example, here we don't have any notions of universal quantifier. We use generalization that for any A, B, and C, this holds. And here we don't have that either, but we have an inherent ellipsis, so an inherent abstraction in representing even one case of my theorem. So I'm going to focus on these: discrete space, algebraic versus geometric theorems. This is perhaps interesting because you would have thought that geometry is the amenable thing to visualize it, but algebra can be too. So I'm talking about natural numbers here, and the ones that can be expressed as diagram and have a parameter, and therefore we're talking about a discrete space because we're talking about these diagrams. But what are the problems? The problems are that these diagrams are concrete in nature. So how do you capture that one example, that the concrete example captures the entire proof for any case, right? For any value of your parameter. And secondly, if you want to talk about the nth case, you would have to use abstractions, ellipses. So you could do that. You could formalize abstractions, but what happens to them when you're trying to spatially manipulate them and cut them in various ways? They are inherently ambiguous and difficult to keep track while manipulating. So I propose a solution to dealing with this problem of abstraction to use schematic proofs. Now, what are schematic proofs? First of all, they use a version of omega rule. And what is an omega rule? Well, it's this: if I can show all the premises for any number, then I can conclude the universal statement. Obviously, if I'm trying to automate this, that means I have to prove an infinite number of premises, which is no good for automation, so I have a problem here. So the solution is to use the constructive version of the omega rule, where all Pn's are proved in a uniform way. And what does it mean, a uniform way? So, so I get a program for my premise P for a particular variable that proves that premise. And then I can conclude the universal statement. Now, a uniform way, one of ways of finding a uniform way is to find an effective procedure. And in my case, I will be looking for a recursive procedure, a recursive program, which is an effective procedure to satisfy that. And now, obviously, now I no longer have to prove an infinite number of premises, but I just have to find a program that proves every premise for me. Okay? And then the schematic proof is then parametrized in the numbers of steps. So whatever n I give to my program, it will produce me a proof for that premise. Okay? And now this has been done in arithmetic. Okay, first, how do you implement it? Well, you start with some examples, so like number 5 that I showed you earlier, and you find the proof, and maybe number 6, and then you find you generalize what this program is in a kind of informed way, I guess, and then you need to verify that you've done your informed way was a correct way. So you have to verify the procedure that you can see that there's a recursion in there, right? So it's in the meta theory you can prove this. It's been applied in arithmetic, this schematic proofs, and the s to the power of n means the nth successive function of 0. Okay, so we're encoding numbers that way. And you will see, I probably won't have time to go through it, but the point is that the schematic proof, the number of steps that I apply in the proof depends on this parameter, okay? So you can see I was applying here the step case of the addition function n times to get to this, and so on. So the proof will say, do this inference rule n times, do that inference rule once, and so on and so forth. So it's a schematic proof. Okay, and so how can we use this now in diagrammatic reasoning? Well, we can first prove formally examples, concrete examples, interactively with diagrams. Then we automatically extract this proof, which is our intelligent guess, I guess. And then as a computer scientist or as a logician, we need to verify that our procedure was done correctly. So these are the 3 steps. And so in terms of the sum of odd natural numbers, you would take, for example, the case for n equals to 4, and you would cut it into 3. See these 3 cuts into L's. Now that's my result, and then I will do maybe split ends to show that each L is an odd natural number. And so my schematic proof would say I'm going to do L cut n minus n times, which is here is the 3 times. And then for each L, so n times, I'll do split n's n minus 1 times. So you can see that it's parametrized over n. And so whatever n I give it, it will produce me a proof for that particular case. I've implemented the diagrammatic theorem prover, which allows you to prove these theorems in an entirely formal way, where it also checks the correctness. It finds, first you use spatial manipulations as your inference steps. You extract, the system extracts a schematic proof, and then it checks it's correct formally. And the things that I had to address in this process were things like, what kind of inference steps do we have? And here we can see that you can see a direct, I guess, realization of Polya's idea that the right representation makes finding a solution trivial. So if you think of a square, one example, in various different ways of representing it, depends which inference step you're doing to it, that you can transform the representation to the one that makes that a very amenable and a trivial task. So if I'm taking a row away from a square, I'll think about the square in terms of rows, okay? And that's then essentially a trivial step. The representation of the schematic proof, which is the program, is of this format, which, as you can see, it's a recursive program where everything happens in this step case, or I think of it as a step case here, which is a sequence of diagrammatic operations, and then we recurse back. And B could be empty base case. And the dependency of the parameter and the number of steps is a linear function. Again, this is a shortcoming, if you like, because there's plenty of other dependency functions that could be like logarithmic functions or so on. But we found that most of the examples that we've seen, the linear dependency was sufficient. And finally, you need to show that what you've extracted, the program that you've extracted, is a correct one. And for that, mathematicians usually would omit that step, because once they've convinced other people that their program is correct, that's it. They wouldn't go into the formalization or verification in the same way as logicians would. But, you know, since I'm automating a system, I wanted to have this formal correctness too. So I implemented a meta theory, where the proof, the correctness of the proof was checked. So this is not a reasoning about the object level theorem, but it's reasoning about the proof, okay? And here is a whole bunch of examples that this theorem prover could prove. But if you pick up any textbook, you will notice that any maths textbook, that it's a mixture of different types of representation. It's a mixture of formula, it's a mixture of diagrams. So you can't prove everything just with diagrams, because you just can't represent everything just with diagrams. Or you might not be able to convey the message in the most salient way just using diagrams or just using formula. So I was interested in how you could mix different representations when you're proving a theorem. And the idea was really that if I have a theorem and I apply a few inference steps, let's say using symbolic reasoning, sentential representations, but then I come to a point where maybe I could use a diagram to explain that bit better. I just wanted to, you know, change the modality anywhere in the middle of the proof. So to have a true, what you would see in the textbook type of mixed representations. So we started to look into that, and we call this heterogeneous reasoning because we are mixing diagrams and sentences, and in fact, completely different representation to that as well, and I'll show you in a minute. And we found that this really helped us in terms of accessibility and to the diverse stakeholders, if you like, who are trying to do formal reasoning but don't have mathematical background. And I'm not going to go into the details of that because I gave the talk about that in Cambridge last week. But there is a demand for this kind of accessibility in for reasoning. So here's one example of what a heterogeneous proof is. So this is a GIF, right? The format of, so how would you formalize a GIF file, right? So we have a square, some picture of a square, and we want to, it's a contrived example, obviously, but I just want to demonstrate a point. So we have image processing tools that could easily process this and say this is a square and it's of a particular size. So it tells me that the area of it is this. And then I continue doing some, I did arithmetic simplification here, and then I compute a shape. So I ask the image processing tool, what is it? And it tells me it's a square. And so shape X is a square, so I can prove a theorem. So you can see that I was using image processing tool steps and formal steps in the theorem prover. So can you do this kind of mixing and matching in one uniform framework? So for that, you need to design what we call a heterogeneous reasoning logic, which will support this kind of mixing. And inevitably, it might have to have formal and informal steps, because how do you formalize an image processing tool? So if you have two formal systems that you plug in together, then you have a formal guarantee to have a formal proof. But if you want to leverage on the power of tools in other representations, then you might have to give up your requests on formality and just treat them as oracle. And we've heard actually quite a lot about that from the mathematicians last week. We need to create a framework where we can do this kind of thing, and we built a prototype system where you can mix this. I'm going to go quite quickly through this, because the take-home message that I want you to take away is that you can do it. And we've implemented a system, a prototype system, to see it. The formal vehicle that we use is called something that is called placeholders, that we call placeholders. And basically, they're like oracle holes where, you know, I plug in my GIF in this particular language, and that's my parameter across it, that it relates to the rest of the world in this representation. We have inference rules that can work across different representations, and we construct proofs, which basically is what you would expect. You have the entailment across the representations. And the formality you get if you have a translation. If you don't have a translation, then sorry, but what else can you do? But you might still welcome that, because you trust enough natural language processing tool or image processing tool to give you valuable information. So we designed this platform called Mixer, where you can plug in anything you like, basically. You can plug in a theorem prover of any that uses any representation. You can plug in just a representation. It has different types of drivers. And they're basically, these drivers are shaking hands points. The only requirement is that if you want to do proof, you have to have a proof maintaining system. Okay, somewhere where this proof is going to be maintained. So you have to decide who's going to maintain your proof, which of the systems. So you can plug them all together. So what we did was we plugged in Speedit, which is a visual reasoners that we built for spider diagrams, with Isabelle. And those who use Isabelle will recognize that the look of it. And so you can construct proofs using visual steps in the visual reasoner. By the way, the spider diagrams is a complete system for monadic first-order logic without equality. So we know that we have a guarantee that every step is formal, or Isabelle steps, if you like. We tested it also on natural language tools as a plugin with Isabelle. PicProc, we call this, when we plugged in the image processing tool, and we used TP-TP representations, for example, from the theorem provers, and so on. So I will finish now. The two other points that I wanted to make, that where to take this work on is to use visual representations and make them more accessible to the different stakeholders out there, and I talked about this before. So we are using these concept diagrams for representing and reasoning about ontologies. And we are also interested in trying to correlate about what happens in the human brain when they're doing visual reasoning steps. So we're using neuroscience approaches to that, because we have a lot of knowledge about visual perception, but we don't know very much about reasoning. So we are looking at what happens on the biological level in the human brain in reasoning with visual representations, and then comparing when the same type of reasoning is modeled in artificial nets, for example, and then trying to find the correlation, whether one can inform the other, and so on. And the idea is that if we could identify what kind of things people find accessible, we could use this as heuristics when we're building our systems. So, and the challenges in this type of work are finding the right representations, how to deal with huge amounts of data that we have, like when we're modeling the brain. How do we ensure correctness of our human-like reasoning systems? And actually, one of the things that we've been thinking about recently is how do we model people making mistakes and people forgetting information, because there's a functional usefulness in that, and we want to investigate how we can model that in our human-like reasoning systems. So I'm going to conclude here. I've showed you an example of how we can approach trying to build systems that are more human-like in the reasoning process. So yeah, thank you very much.